Okay, good morning. In our lesson today, we're going to look at how you can use a Laplace transform to solve a differential equation. And we're going to concentrate on a first order differential equation in this particular lesson. We need to be using our table of transforms, and in addition we need this one formula. If you take the Laplace transform of y prime, it's the same as having s times the Laplace transform of y minus y at 0. And this, of course, will be a constant. It represents the initial value of y. Okay, so we're going to get started. I have 5 examples that I'd like to present, so it might get to be a rather lengthy video, but obviously feel free to pause it when you need to. Okay, so here we go. The first equation is y prime minus 3y is 0, and y at 0 is 1. So what we want to do is find the function y that satisfies this equation. Okay, so we begin by taking the Laplace transform of every term. So of this term and this term. And we would also take the Laplace transform of 0, but the Laplace transform of 0 is 0. So we begin and it would look like this. So I'm taking the Laplace transform of y prime minus, then we'll be taking the Laplace transform of 3y, but this is the same as 3 times the Laplace transform of y equals the Laplace transform of 0 is 0. So we begin like this. Now here is where we make use of the formula. So we remove the Laplace transform of y prime, and in its place we put these two terms here. So it will be s times the Laplace transform of y minus y at 0. And then the rest of the equation. Okay, but in this position here, y at 0, we can put 1. So it becomes minus 1. Okay, now that we've used the formula, our objective is to isolate the Laplace transform of y. Okay, so how would we isolate that? Well, 2 terms contain it. So those 2 terms will stay on the left side. So this is like collecting like terms. So this term will stay on the left side, as will this term. And on the right side, we'll be moving this term. And of course, it will now be positive 1. Now we're still trying to isolate Laplace transform of y. So that would suggest that we factor it out of these 2 terms on the left side. And if we do that, what would be in the bracket here? S minus 3. Just like that. And you can check, if you were to open up this bracket using multiplication, you'd get this line back. Continue to isolate the Laplace transform of y. How do you do that? You would divide both sides by s minus 3. And so now we have the Laplace transform of y isolated. This is the moment when we can use our table. If the Laplace transform of y is equal to 1 over s minus 3, we can determine y with our table. So what we have to do is find this in our table. So let's have a look at our table. I think that you'll see it compares with number 3 right here. So I'm going to write down that this compares with number 3. And what is our a value? Well, it's s plus a, and here we have s minus 3. So the value of a is -3. So how do we go from Laplace transform of y to y? We simply move left in the table and we'll write this, e to the -at. But since a is -3, this becomes e to the 3t. And we're done. We've now solved it. So this function satisfies this equation. You can see that it would be true. What is y prime if this is y? Y prime would be 3 times e to the 3t, right? The derivative of this would be 3 times e to the 3t. So we'd have 3 times e to the 3t minus 3 times e to the 3t, and that certainly is 0. Is y at 0 equal to 1? This means y is 1 when t is 0. And if you put 0 in here for t, you'd get e to the 0, which is 1. So this one equation of y equals e to the 3t satisfies both this differential equation and this initial condition. Should I just show you that really quickly? Why not? Okay, so we're going to first demonstrate that the function satisfies the differential equation. What would y prime be? It would be 3 e to the 3t minus 3 times y is e to the 3t. Is that equal to 0? Yes, so we end up with left and right sides equal. And then the other thing we want to check is y at 0 equal to 1. Well, remember y is e to the 3t. So what we'd be doing is substituting t equals 0. So y equals e to the 0, which is certainly 1. Okay, so you can see that this equation does satisfy the original differential equation as well as the initial condition. And I won't check all of them. I only want to show you what it means when you find your answer. It means you found the function that satisfies the original differential equation and the initial condition. Okay, but you are done once you have this function for y. So let's continue and do our second example. Okay, so here is our next example. So we begin by taking the Laplace transform of each term. So 2 times the Laplace transform of y prime plus the Laplace transform of y is the Laplace transform of 1. So that's how we begin. And then right here, instead of the Laplace transform of y prime, we put s times the Laplace transform of y minus y at 0. Now that is a binomial, right? This is a binomial. And so if it is doubled, the whole binomial is doubled. So what we should do is put a 2 and then a bracket with the binomial inside. So it's s times the Laplace transform of y, and then remember it's minus y at 0. Y at 0 is 3. Okay, so we have this binomial replacing the Laplace transform of y prime. And now I'll just write out the second term. And here we can actually take the Laplace transform of 1. Now the Laplace transform of 0 remained 0. But the Laplace transform of 1 is 1 over s. So this is what we have thus far. Okay, now remember the objective is to isolate the Laplace transform of y. So first I'm going to double here. So again, right here, we have to make sure we're also doubling this y at 0 term. So that is now a 6. Okay, time to collect like terms. So these two terms will stay on the left. This term will move to the right. So we're going to have plus 6 over here, times common factor. So if the Laplace transform of y is removed as the common factor, we will have 2s plus 1 in this bracket. Okay, again, quick check. If you open the bracket up, you should get back this. Okay? The last step is to divide both sides of the equation by 2s plus 1. So when I do that, I'm just going to keep these terms separately. So I'll show you what I mean here. So 1 over s gets divided by 2s plus 1. And that looks like this. And 6 also will be divided by 2s plus 1. So I've kept them separate so that I will then be looking up two different transforms in our table. Okay? So when this term is divided by 2s plus 1, 2s plus 1 simply joins s in the denominator. Okay, then I also divided 6 by 2s plus 1. And then it's time to look at the table and try to decide where we might find these transforms. Okay, so let's have a look. In fact, this one is the same one we used in the last problem. It's number 3. Okay, the only problem is the coefficient of 2 here must be eliminated before we try to use number 3. What about this one then? It has s and then multiplication by 2s plus 1. That will actually be number 4. But again, we have to have a coefficient of 1 here on s before we use number 4. So that leads me to my next step, which is changing these fractions so that we have just a 1s here and a 1s here. So how do we do that? We just have to divide the bottom of each by 2. Okay, so I'll do this one here because it's a little easier. So I'll start with this one. So we divide the denominator by 2. So that would be s plus 1/2. Well, if you divide the denominator by 2, you must also divide the numerator by 2. So these are now equivalent fractions. Okay? So I have to do the same thing here. In the same way, you just divide the denominator by 2. That doesn't change that s. It only changes this binomial. If I also divide this by 2, then overall I will have divided by 4. Okay, so all we do is we divide by 2. So that means only dividing the one term by 2. Once we divide now the denominator by 2 like this, we also have to divide the numerator by 2. So this fraction is equivalent to this fraction. Okay, and now, yes, we will be using transforms 4 and 3, respectively, and for each, a is positive 1/2. Okay, so we're going to be using these transforms with a equal to positive 1/2. Now let's have a quick look. For transform 3, with a is 1/2, in the numerator should be a 1. So I should put a 1 here and push 3 out front. For number 4, if 1/2 is here, 1/2 should also be on top. So that one is set up perfectly. Okay, so I'll just show you how we can fix the second one. So that one's already perfect. And for this one, all I'm saying is this is 3 times 1 over s plus 1/2. So in other words, we'll have a coefficient of 3 for that term. Okay? Right, take a look. This is equivalent to this. And now it's time to use the table and write out our answer. Okay, so let me just make sure. Yeah, I think you can see all of that in the display. Oh yeah, perfect. Okay, so let's do this one. We're starting with number 4, and we have a equal to 1/2, so we're gonna write 1 minus e to the negative 1/2 t. 1 minus e to the negative 1/2 t, or to the negative t over 2, same thing. And then we have plus 3 times, now we do a number 3, which is here, e to the negative 1/2 t, or again, t over 2, like that. And then finally, for this question, these are like terms. So we have negative 1 of them plus 3 of them. So overall, we have positive 2 e to the negative t over 2. Just like that. And that's it. Perfect. We've solved it. Okay, so these are long problems for sure. And you have to be very careful because of the number of steps. Here, this is a very common mistake, as I said. When you replace this with the binomial, it's important to bracket the binomial if there's a coefficient in the front, because that affects both of these terms. Okay? All right, let's keep going. The more we do together, the better off you'll be, right? Okay, so let's go on. This is the third one I'd like to try with you. So we get started. The Laplace transform of y prime plus 5 times the Laplace transform of y is the Laplace transform of e to the 2t. Like that. Right here, we replace Laplace transform of y prime with s times the Laplace transform of y minus y at 0 or 2. Let's just write in our next term. And then here we'll write the transform of e to the 2t. That's our number 3, right? So the transform of e to the 2t. So a must be negative 2. So we'll have 1 over s minus 2 on the right side. Okay, so if you want, you can indicate here as well that we just used number 3 with a being negative 2. Okay, perfect. Now we continue to isolate the Laplace transform of y. So these two terms stay on the left. This one moves to the right. S times L at y plus 5 L at y is 1 over s minus 2 plus 2. Okay, so we've got these two terms on the right side and 2 on the left. Common factor in the bracket, s plus 5. This is the point at which we will divide both sides by s plus 5. So I will divide these two terms separately. So we're going to have here s minus 2 and s plus 5 now in the denominator. And under the 2 will be s plus 5. So that's what we get when we divide all terms by s plus 5. And now, in order to find y, we have to transform these two terms. Okay, you know this is going to be a number 3, and we should push the 2 out front, leaving a 1 here. What about this guy? Number 9, look, s plus a, s plus b. So we can use number 9 on this one. Our a value is negative 2, and our b value is positive 5. Okay, so that will allow us to figure out what the numerator should be. So I'm going to write down our plan. We're planning to use number 9. We have a is negative 2, while b is positive 5. The numerator, therefore, should be b minus a. What is b minus a in this case? It's 5 minus a negative 2, so it's 7. So up top here, I need a 7. And I don't have a 1, but who cares? I'm going to put a 7 there because that's what I need. How do we compensate for that? The fact that we went from this fraction to this fraction. Well, if we multiplied here by 7, we compensate by putting 1 over 7 in front of that, right? Check this out. Now this is still equal to this. You could see the 7s could cancel and we'd get this back. Okay, so you figure out you need the 7 in the top, so put it there. That's easily compensated with a coefficient of 1/7. Okay, this one here, we said that we would use transform 3 with a equal to 5. And the only trick with this one is that we really just want a 1 on top. Right? For number 3, it's just a 1 on top. So we have a 1 on top now. So the 2 can go out front. Check. Is this equal to this? Yes, it is. 2 times this fraction is this fraction. So whatever you're doing here out front has to make the overall fraction equal to the one you had, right? Always check. Does this equal what we had? Does this equal what we had? Okay, now we're perfectly ready to do the transform. So we're going to have 1/7 as the coefficient of, so we're using number 9, so it's a binomial. I'm going to put a bracket, and now I write e to the negative at, so that's e to the positive 2t, minus e to the negative bt, so that's e to the negative 5t, okay? Plus a coefficient of 2 in front of, we're using number 3, with a equal 5, e to the negative 5t. Just like that. Okay? Okay, so these are like terms here though, so I might as well monkey around with this a bit. So I'm going to bring in the 1/7 here. Okay, so that I can collect these now. So if we have 2 minus a 7th, 2 minus 1/7 of them, that's the same as 14/7 minus 1/7 seventh. So that's 13/7 of that e to the negative 5t. Here it might be nice to then common factor 1/7. And that's your final equation for y. All right, and that one is now solved. Okay, so I hope that you're following along okay with these in terms of the process, right? I know that they're long and there are many, many steps, and it certainly will take practice. Okay, let's continue. It's 25 minutes already. That's okay, we'll keep going. Rather than making 2 separate videos, I might as well continue. Okay, here we go. Here's our next problem. We begin in the same way. So we do the Laplace transform of y prime plus 2 times the Laplace transform of y is the Laplace transform of the cosine of 2t. Right here, we replace this with s times the Laplace transform of y minus y at 0, but y at 0 is 0. Then we have plus 2 times the Laplace transform of y equals, and now we'll take the transform of the cosine of 2t. We're using number 5 with a is 2. Okay, so if you want to reference that here, so what will that give me? S over s squared plus, and I could leave it 2 squared or change it to 4. Whatever you like there for now. Okay, so there we go. We're all set. What happens next? Collection of like terms. Well, that's just a 0 anyway, right? So you can completely ignore it. So we already have like terms collected. We've got these 2 terms on the left. So we should common factor the Laplace transform of y. So that'll leave me with s plus 2. Okay, so this is what we have. So far again, we took the transform of each and every term using the table here. Number 5 with a is 2. Here we replace with this binomial. Okay? And now we're isolating the Laplace transform of y, which means dividing by s plus 2. And this is what we have. So we have one fraction. The denominator is s plus 2 multiplied by s squared plus 4. Now the key is, can we find that in our table? Well, it's 2 binomials multiplied together, which is only found here. However, this is s squared, and we do not have that. So this is not in the table. So I think you're aware that that means we're going to have to use partial fractions. So we're going to split this into 2 fractions, one with a denominator of s plus 2, the other fraction with a denominator of s squared plus 4. So let's get that set up, okay? So the sum of 2 fractions okay, so we're changing this into the sum of 2 fractions, one with a denominator s plus 2, one with the denominator s squared plus 4. Now we have to put in the correct numerators here. If this is a linear factor, then up top will be a single letter. So we start with A. This is quadratic. It's a quadratic factor because we have s squared. Okay, so we have a binomial with s squared. So that means up here we need a linear term. So it means of the form b times s plus c, like that. So what we need to do is take this now and use it to find out the values for A and for B and for C. So how do we do that? We say that S here, the original numerator, is equal to A multiplied by s squared plus 4 plus the bs plus c, which is a binomial, so it needs to be bracketed, is multiplied by the binomial s plus 2. Okay, so this is how we make our main equation. So A multiplied by s squared plus 4 plus bs plus c multiplied by s plus 2, like that. And now we start solving. So we begin by identifying any roots. The only roots are s equals -2. Okay? So so we begin with that. We'll substitute s equals -2. Start by substituting it on the left side. So s is replaced with -2. On the right side, what will happen if we substitute -2? Well, -2 all squared is +4. So in here then, we will have 4 plus 4 or 8. Okay, and then it would be plus 0. Because remember, you're putting -2 here also. So this is 0 times this term. Okay, so all we get is this. And so from that, we get A is -2 over 8. -2 over 8 reduces to -1/4. So now we know the value of A. And the problem here is we're out of roots. There is no s value that makes s squared plus 4 equal to 0. So this means that to find B and C, we can use coefficients. Let's try the highest coefficient, which is s squared. Okay, what is the coefficient of s squared on the left side? Well, there is no s squared term, so it's 0s squared is, and what is the coefficient for s squared on the right side? Well, there's one here, but there's also one here. So it's as squared plus, there's a plus sign in here, bs squared. So we get 0s squareds are equal to as squared plus bs squared. And from that, we get the equation 0 is a plus b. And since a is -1/4, this means b is 1/4. So now we know b. And then when it comes to finding the last letter, you could either arbitrarily substitute any value you like, or you could look at more coefficients. So I'll just arbitrarily substitute. I'm going to go with s equals 0 is what I substitute. And that's a nice easy one to substitute. So we put s equals 0 here and we get 0. If we put s equals 0 here, we're going to get a times 4. Plus, and if we put s equals 0 here, this bracket just becomes c. And s equals 0, so this bracket just becomes 2. So we end up with this equation. 0 is 4a plus 2c. And a is -1/4. So 4 times -1/4 is -1. So we end up with 2c is 1. All right, and from that, of course, c is 1/2. And now we have our values. And what we do is we put them here, here and here. And I will show you what that looks like. So we have Laplace transform of y is, so we have a over s plus 2, so negative a quarter over s plus 2, plus now we have b times s plus c, so 1/4 s plus a half, and that's over s squared plus 4. Perfect. And at this point, it would be time to use our table. Okay, we know this is number 3, and all I have to do is scooch the negative a quarter to the front. So let's concentrate on this guy. Where are we going to find it? The denominator is s squared plus 4. So where do we have that? We have that here and here. But look at the numerators. One has an s on its own, and the other has an a on its own. Well, we've got a term with s and a constant, so we have to split this one. Okay, so I'm going to do that now in the next step. Oops, it's supposed to say negative a quarter somehow. Huh. Okay. So what I'm saying is we're going to keep 1/4 s as the numerator of 1 and a half as the numerator of another. Okay, this is certainly equivalent to this. Okay, that's how we know that this is a permitted step. These are equal. Okay, now we've got to start thinking about what the tops should look like though. So we already said here we need just a 1 because we're using transform 3. Okay, so let me just slide this up just a little so we have a little more room. I got to move the negative a quarter in order to use transform 3. Now, what about this one? Where's this going to be? This is the one with the s, so it's here. So all I have to do is move the quarter again because the s should be alone. What should be up top here, though, is the key. It should be a. Remember, a is 2. That was established right at the very beginning of the problem. Okay? Or you can just see it again anyway. 4 is a squared. So a is 2. So I should have a 2 up top here. So I'm going to put a 2 there, and then we'll compensate out front. So I'm going to get another paper, because this is obviously a long problem. Okay, so here's what we're doing. We're moving the negative 1/4 to the coefficient here. And we're moving the positive 1/4 so that it's the coefficient here. And for the last one, we need a 2 up top, so we're putting a 2 up top. And we'll have to figure out what to put in front of it in a moment. So let's have a look real quick. I want you to make sure you understand that this is exactly the same as this. This is exactly the same as this. This is the one that's changed. It went from a half to a 2. So how can we make sure they're the same? We have to put 1/4 here, right? 1/4 times 2 will give us back the half that we need. Okay, and now we have it perfectly set up to use our transform number 3 right here with a equals 2. This one is our transform 5. A is still 2, okay? And lastly, this one will be number 6 with a still 2. So we can write out our answer here. The coefficient of the first term is negative 1/4, and that's in front of e to the negative 2t. Then we have plus a coefficient of 1/4 in front of the cosine of 2t. And lastly, another coefficient of 1/4 in front of the sign of 2t. And that's it. That one is now done, and it's perfect. Okay? It's kind of demanding that you common factor either a quarter or negative a quarter here, whatever you like. Maybe I'll take out a quarter, so I'll have cos 2t plus sine 2t minus e to the negative 2t, like that in my final answer. Okay? All right, so that was a nice long question that required the use of partial fractions. Let's do one more problem together. Okay, we're gonna move on. This is problem 5. Let's get started. So we have y at 0 is 0. So we start like this. 4 times the Laplace transform of y prime minus 2 times the Laplace transform of y is the Laplace transform of t. After the coefficient of 4, we would have a binomial. So it's important to have a bracket. In it will be s times the Laplace transform of y minus y at 0. In this case, that happens to be 0. Write out the next term. And then we're here, the Laplace transform of t. This is number 2, the Laplace transform of t. So n minus 1 is 1, right? Because the exponent is 1. If we have t to the 1, the exponent is 1. So we have n minus 1 is 1, which means that the denominator is 1, right? N minus 1 is 1, so the denominator is 1 factorial or 1. So that's perfect for number 2. It means n is 2. If n minus 1 is 1, then n is 2. So we write 1 over s squared. Okay, next step. So we just use transform 2. The Laplace transform of t is 1 over s squared. We'd open this up now, right? But that's a 0, so we're just gonna get 4s Laplace transform of y minus 2 Laplace transform of y is 1 over s squared. Common factor, 4s minus 2. Finally, divide. And we have a denominator that is now s squared times 4s minus 2. Do we have that denominator in our chart? An s squared in front of a linear term. This would be like an s plus a, no problem. But do we have one with an s squared in front of s plus a? Oh, look, an s squared. Oh, no. This is also squared. That was a good try. We do not have this denominator in our chart. What does that mean? Dun, dun, dun. Partial fractions. Okay, so here we go. Partial fractions once more. How many fractions do we need to set up this denominator? Okay, do you remember that s squared is treated like a repeated linear factor and requires 2 fractions, one with a denominator of s and a second with a denominator of s squared. And since this is considered a repeated linear factor, in the numerator is a single letter for each. And then, of course, we need one more for 4s minus 2, which is also a linear factor, so requires a letter up top. Okay, so look, here's the denominator. So we need an s squared, and a 4s minus 2. Again, s squared is considered to be a repeated linear factor. So if it was s cubed, then just for the s cubed part, you would need 3 fractions, one with a denominator of s, one with a denominator of s squared, one with a denominator of s cubed, and the numerators would be a and b and c. Okay, repeated linear factor. Okay, but we've got this one set up now. We do our main equation. So we take 1 and we set it equal to a. Now what does a need to be multiplied by? It has an s under it already, and we're comparing with this denominator. So it needs one more s and a 4s minus 2. Now we do this, plus b. What does b get multiplied by? Well, it has s squared already, and we are comparing with this denominator. So it only requires the 4s minus 2. Plus c. What is c multiplied by? Well, it has 4s minus 2 under it. Comparing here, it's missing the s squared. So that's the correct setup. Do we have any roots? We have 2 roots actually. S equals 0, which is certainly a root, right? S equals 0. Okay, so we can start with that one. And after that, what other 0 do we have? Well, if 4s minus 2 is 0, then 4s is 2 and s equals 1/2 is also a root. So we're going to start like that. That'll give us 2 of the letters right away. Substitute s equals 0. Left side stays 1. This would be a times 0, so that term is gone. So we're here. B, it's 4 times 0 minus 2. Okay? And then it would be plus c times 0. So the only non-zero term is here. And we're substituting 0 here. So we end up with b times negative 2. So what does this mean? b is 1 divided by negative 2. So b is negative 1/2. Let's substitute 1/2. Left side stays 1. Substituting 1/2, this term will be 0, this term will be 0. The only non-zero term is here. And it's c times 1/2 squared is 1/4. So what is c then? It's 1 divided by 1/4, which means it's actually 4. Okay, and then lastly, we want to know the value of a. We could substitute another value arbitrarily, maybe s equals 1, or we could look at the coefficients. I'm going to do the coefficients of s squared. On the left, we have 0 s squareds. Where are the squareds on the right? One here, it's 4 times a times s squared. No square here, but one more here. Plus c times s squared. So we end up with 0 s squared is 4 times a times s squared plus cs squared. So from that, we get the following. 4a plus c is 0. C is 4, so now we know 4a plus 4 is 0, so this means 4a is negative 4. So from there, you can see a is negative 1. Okay, so I've got all my quantities determined. So I pop them back up into here. So the Laplace transform of y is negative 1 over s plus negative 1/2 over s squared plus 4 over 4s minus 2. and then it would be time to try our table. Now, you should know by now this 4 can't stay. So I'm going to adjust this right away. Divide all these terms by 4. Okay, so that corresponds to dividing the bottom by 4 and the top by 4. Because this is just a one single term. Okay, so I'm going to do that. Certainly. This guy, you know, it's the same as having -1 times 1 over s here, right? And I just did that because 1 over s is in the chart. And we had -1 over s. So I just moved the -1 over. And this is the reverse of what we used right at the beginning here. So I'm going to move the -½ and leave 1 over s squared here. Okay. So basically I'm trying to get a 1 in the top there. Same thing here. I wanted a 1 in the top. So the -1 and the -½ are the coefficients. And this one, what did we say? We had to have a single s there, not a 4s. We need a coefficient of 1 on the s. So this becomes s minus ½ and this will be a 1. So again, we divide the bottom by 4. That gives you this, and the top by 4. And now we can use our transforms. So right here, that is number 1. Right here, that is 1 over s squared. That is number 2. And this one, of course, is number 3. Right here, that's number 3. With a equal to -½ So, time to transform. Y equals, so this will be -1 times 1. See, the transform of 1 over s is 1. So -1 times 1, that's just -1. Then we're going to have a coefficient of -½ in front of the transform of 1 over s squared, which is t. Okay, because n is 2, so this becomes t to the 1 over 1 factorial, which is t. And then a plus sign. And lastly, number 3, with a equal to -½ we get e to the 1/2 t, or e to the t over 2, whatever you prefer. And that's it. It's perfect. Okay, so 5 examples in total were presented today. The last 2 required the method of partial fractions. Please, please, please start practicing solving these questions. I've got some suggested problems outlined for you in Blackboard within that Module 3 folder. Okay, thanks so much and have a really nice day.